This problem involves centripetal force, centripetal acceleration, and gravitation. We're going to consider the Hubble telescope, and some of the statistics about the telescope are given here. Completing one orbit of the Earth every 95 minutes. We're going to assume the orbit's a circle. It's not really a circle. We're not going to worry about the influence of the moon on the orbit or the sun. We're going to let the Earth be a sphere with a given mass and radius. We want to make three calculations. We want to calculate the distance of the Hubble telescope from the surface of the Earth. We want to know its altitude. How far above the ground is it? We want to know the speed of the Hubble telescope in its orbit that we're assuming to be circular. And we want to compare the kinetic energy of the Hubble telescope with a car's kinetic energy. So let's get into our problems here. And it's always good practice in making a problem is to make a sketch. Doesn't have to be a great sketch, but make a sketch and label things in the sketch. Here's the H stands for the Hubble telescope, and its velocity. We're going to view this in a situation where it's orbiting counterclockwise from the top view here. And take a look. F sub c is required. The centripetal force is required to make the telescope move in a circle. What's the altitude? Well, the altitude, we need to know the radius of the orbit, and we need to know the Earth's radius, and we'll subtract those two. The altitude is just this gap here between the surface of the Earth and the path of the orbit. The force of gravity is supplying the centripetal force. There's no friction out here. There's no string attached to the Hubble telescope that would pull it towards the center of the circle. So the force of gravity, we calculate the force of gravity with the gravitational constant. We multiply the two masses together, the Hubble telescope and mass of the Earth. We divide by the square of the distance between the centers of these two objects. And then we have, for centripetal force, the mass of the object in motion, the square of the speed, the magnitude of the velocity, and divide by the size of the orbit. So you can see, you ought to inspect this and see some things that will cancel here. We have m sub h on both sides of the formula, or the equation here, so that's going to cancel. And one factor of r is going to cancel, but we'll save that because I want to make a substitution. I'm going to substitute that the velocity, the speed, is distance divided by time. So for v, I'm going to put in 2 pi r divided by time, and that's done here in the square brackets, and we have to remember to square that. The square of the speed, square of the magnitude of the velocity is up here. I have to be faithful and retain that square. So you ought to inspect this, perhaps pause the video and see how you'll process the symbols here. How will we move to our next expression? Well, I'm just copying it here. But when we square 2, we get a 4. We square pi, we get pi squared. Square r, we get r squared. The t becomes t squared, and it's a division, so it goes down here with the r. How can this be simplified? How can it be simplified? Well, I'm going to solve for the cube of r. So the cube of r, and maybe I should go back and just show what I'm doing here. Multiply both sides by r squared, I get r to the 4th, but we're dividing by r, so that'll be an r cubed. And then I want to take everything that's multiplying on r cubed to the left side by dividing by 4, by dividing by pi squared, and multiplying by t squared. So we'll see if we look similar over here. Gravitational constant, mass of the Earth, time squared. This time is in seconds, is the unit, and 4 pi squared. Well, you can look up the mass of the Earth, the universal constant of gravitation, and the orbit time, 5,700 seconds. We put these numbers in. You should pause this and do your own calculator, but g/MET squared divided by 4 pi squared produces 3.2802 times 10 to the 20th. I don't round intermediate calculations. So we take a cube root of that. We get this for the size of the orbit, roughly 6.9 million meters, or 6.9 thousand kilometers. What's the altitude? Well, the orbit radius, we have to subtract the Earth's radius, and I get 5.27 times 10 to the 5th meters. That's this gap distance between the blue Earth and the line of the orbit. And if I convert this to miles, if you divide by 1609, you can convert meters into miles, 327 miles. That's the altitude if we assume a circular orbit for the Hubble telescope, 327 miles up. Not that far. Well, what about the speed? Well, for speed, we need distance divided by time. So the circumference of the circle would be our distance, 2 pi r, and divided by the time. We found in the previous slide the radius of the orbit, so I keep that and put in the time of 5,700 seconds. If you again pause the video and pull out your calculator, I came up with a speed of 7.6 times 10 to the 3rd meters per second. And I could round that off to 3 places, 7.60 times 10 to the 3rd. If you convert that to miles per hour, roughly, and to do that, you would 1 mile per hour divided by 0.447 meters per second. 1 mile per hour divided by 0.447 meters per second. Use that conversion factor, so we get about 17,000 miles per hour. And that's typical for things in low Earth orbit. This is a low Earth orbit. My drawing is not to scale. But what about the kinetic energies? The kinetic energy of the Hubble telescope, 1/2 mv squared is our formula for kinetic energy. We will have to put in the mass of the Hubble telescope and put in the magnitude of the velocity of the Hubble telescope in its orbit. So we know these numbers from previous pages, given information on the mass of the Hubble telescope, the speed of the Hubble telescope in its orbit, and later we'll need this for the kinetic energy of the car. I'm picking just sort of a run-of-the-mill car, 2,000 pounds, 907 kilograms, and the 60 miles per hour, converted to meters per second, is 26.8 meters per second. So doing 1/2 mv squared for both of these objects, first the Hubble telescope and then the car, or first the car and then the Hubble telescope, I found 3.26 times 10 to the 5th joules. That's 326,000 joules. Sounds like a lot of energy. But look at the Hubble calculation. 3.2 times 10 to the 11th joules. This is 321 billion joules. It's larger by a factor of 1,000,000 compared to the car kinetic energy. Well, we ought to expect it to be larger. First, because the mass of the Hubble telescope is larger than the mass of the car, roughly by a factor of 12. But what makes the big difference, kinetic energy is proportional to the square of the velocity. And the Hubble velocity is larger than a car's velocity at 60 miles an hour by a factor of 283. So we get a much larger kinetic energy than we have for a car. How did the Hubble telescope get this energy? A rocket propelled it into orbit, and hopefully you're not driving a car that has a rocket engine. If you'd like to see more of these physics videos and astronomy videos, there's a list of my YouTube videos at gpclements.com. This is a simple website. It groups the videos by topic. The video will have a title and the length of time for the video, a short description of the video, and perhaps most useful, it has a direct link to YouTube. So you don't have to search on YouTube for the video. You can just click on the link and go there immediately. All this content's free. You don't register. You don't give your email address, any information. And my website does not put cookies on your computer. Keep working physics problems. Ask your instructor if you have questions.